Good morning, everybody. Well, I welcome you to the fourth day of the first Balkan summer school for astrophysics and astronomy. Now I want to thank Professor Stanislav Milosevic of University of Belgrade. The title of his speak is a brief introduction to extragalactic astronomy. Thank you.
Thank you. First of all, I want to thank the organizers for inviting me, and it's a very great pleasure to be here today, and I know how much effort it needs to organize such an event and to bring students from different Balkan countries to one place in the middle, actually at the end of the summer break, and I want to thank you for coming here, and I hope that this lecture will be interesting to you. I will try to summarize something that you already heard in the previous lectures, and also to give you some maybe new view on the galactic formation and galactic morphology, evolution of galaxies, and evolution of the universe as a whole. So the title is Introduction to Extragalactic Astronomy. I put this extra in the brackets because there is not quite difference in studying specific galaxy or our galaxy Milky Way and the galaxies as a group, as a building blocks of the universe. You will see later. So can you tell me what can you see in this image? Louder, please. Yeah, that's a Milky Way. And if we see this image, we can see some light in the middle of the image and some dust, some, of course, some stars. And can you tell me also, are there any extragalactic objects on this image? What would be your guess? Yeah, in the image. For example, are there any chance that we can see from this point, from this place, any extragalactic object? Probably many of the stars. Probably. Many of the stars. Yeah, but those stars and all those objects on the image are actually in our galaxy. So the most probably that you will see only objects in our galaxy by naked eye, of course. With telescopes you can see many other things. Yes? Yeah, we can see only several extragalactic objects. That's true. We can see only several extragalactic objects, and one of them is Andromeda Galaxy. She's on the, now it's on the northeast part of the sky above the Cassiopeia constellation. So yes, many of these objects are in our galaxy, and of course you can see a lot of empty space between these stars. Nice. So this is our galaxy, the Milky Way, and what we see on the previous image was the disk of the Milky Way. It was observed by the ancient people, ancient Greeks, and later Arabs and Roman people, and so on. And after a few centuries ago, Herschel gave the first kind of description of the Milky Way. Of course, we had some religious descriptions previously of the Milky Way, but the first important scientific description of the Milky Way was given by Herschel, and this is the map that he drew it as a Milky Way, and he drew it by star counting. So he was actually counting stars in the different area of the sky, and constructed this map. And you can see this map in one very nice textbook. It calls An Introduction to Modern Astrophysics. It's a pretty large book. With various topics written by Carol and Osley, so my recommendation to read some chapters of this book, and I will give you references at the end of the lecture. And in the history of astronomy and the history of science, and also Milan was talking about that a few days ago, our ideas about universe, about world, about our place in the world were evolving through time. And until 20th century, we didn't know, are there any other galaxies except Milky Way? Are we alone? I mean, is Milky Way the only galaxy in the universe? Is it a whole universe, or we have a bunch of galaxies? And when we built some telescopes with, let's say, 1 meter in diameter, we could see some new extragalactic objects. One of them is, of course, M31, a little bit better than before. And then we opened the debate, are those faint objects that we can see in our galaxy, are they outside from our galaxy? Are there some extragalactic objects, or there are some nebulas in our own galaxy? So there was a the great debate in 1920 between Curtis and Shapley. And Shapley stated that all nebula are part of the Milky Way. And Curtis said that Andromeda, which is one of the nebula, are extragalactic objects. But of course, when he was calculating distance to Andromeda and to other faint objects, he made a lot of errors because he didn't calculate gas and absorption by gas and dust in the Milky Way. So that objects looked far away than they really are. And we can say that in that years, 20 years of the last century, so about 1 century ago, we can say that the cosmology is born. So when we are talking about cosmology as a part of astrophysics, or not a part of astrophysics, but cosmology as a specific discipline, a scientific discipline, we can say that it is born in about 100 years ago. So 100 years ago, we didn't know. Are we have only one galaxy, and is it the whole universe, or we have a bunch of galaxies? Now we know that we have thousands and millions and billions of galaxies in the universe, and they're different by their morphology, masses, and so on. And I will speak about that. So after that, we actually knew that we have different, and we have many galaxies, and Andromeda is, fun fact, more massive and a little bit larger than the Milky Way, and it's the most massive galaxy in the local group, in our let's say galactic neighborhood. So when we are observing the universe on the large scale, so we can say that galaxies are building blocks of the universe. So they are like cells in human beings. So they are really the most important objects when we are talking about large-scale structures and organization of matter on a large scale. So when we talk about galaxies, we can say they can differ in morphology, in mass, in activity. Some galaxies are active galaxies. Some galaxies we tag like a normal galaxies. And when someone asks you what is galaxy, you can say that it's a stellar system with interstellar medium. Interstellar medium is consisted by gas, dust, magnetic field. And of course, we will see later around that visible part, around the baryonic part, we have a dark matter halo. You also heard about dark matter in previous lectures. And in our neighborhood, galactic neighborhood, we have around 50 galaxies, 55. The largest one is Andromeda, or M31. It's a large spiral galaxy with a mass 10 to 12 solar masses. And the second one is Milky Way, and the other galaxies are mostly dwarf galaxies, which are satellites of Andromeda and Milky Way. Does anybody know what is the approximate radius of the local group? Is it a kiloparsec or 100 kiloparsecs? Or okay, it's a megaparsec. So 1 million parsecs is approximately radius of the local group, and radius of the diameter of Milky Way is about 30,000 kiloparsecs. So it's 100,000 light years, and Andromeda is far away from us, about 700 kiloparsecs. So it's a large distances, of course, but in the cosmic scale, they're not large distances. It's a typical distances. Okay. So the first thing, I divided this lecture in 3 parts. The first part will talk about morphology of galaxy, the second part about interactions of galaxies, and the third part will be the formation and evolution of galaxies. So do you know, okay, there is a title up there, Hubble's tuning fork, and this was a first map of galactic morphology, which was published in this famous Hubble's paper from 1926, Extragalactic Nebula. And I hope you all already saw this image. we have different, do I have a pointer here, sorry? On the right, okay, thank you, it's a black, everything is black, so nice, let me, nice. So we have different morphological types, and he actually made a difference between types by their shape. So when we talk about morphology, we talk about shape. And on the right side, on the left side of this image, we have elliptical galaxies. They are mostly spherical or ellipsoidal, and they are tagged from E0 to E7. It depends under which angle we are observing these galaxies. Then we have some lenticular galaxies that are intermediate type between ellipticals and spirals, and we have these parts of the fork, or these two branches of spiral galaxies. Despite do they have a bar or they don't have a bar. So these SBA, SBB, SBC are spiral galaxies with a bar, and this one is without bar. And of course we have these some kind of irregular galaxies. Hubble firstly thought that this is some kind of evolutionary array, so he named these galaxies like early type galaxies. And we know that actually they are not connected, evolutionary, they are not connected with the spiral galaxies in the sense they are older than them. These galaxies are actually younger than these one, because these galaxies are formed in mergers of the spiral galaxies, irregular galaxies, and dwarf galaxies. So elliptical galaxies are just tagged like early type galaxies, and these spiral galaxies are tagged like late type galaxies, but they are not any time evolutionary connection between these two types. In spiral galaxies, the most prominent structure is a galactic disk, and we have spirals in the disk. And we also have bars can be formed by the gravitational instability in flybys or merger events and so on. And probably because we cannot directly observe Milky Way, because we cannot travel from the Milky Way and then observe it from some distance. And but observing other galaxies, for example M31, and which is another name for Andromeda, and other spiral galaxies, we can conclude something about the Milky Way. So the Milky Way is probably this type of galaxy, SBB. So a spiral galaxy with a bar. And I will tell you some more thing about each morphological type. So spiral galaxies, I already said, the most prominent structure is galactic disk. Then we have some spherical. Sorry? No. But it's similar to us. Does anybody know what is this galaxy? Which galaxy? Yeah? No, it's not Sombrero. It's very neat. We already mentioned this galaxy several times. It's Andromeda galaxy. It's our neighboring spiral galaxy, and we can see it in detail actually with some angle, of course. And the most prominent structure is galactic disk. So, and we have spiral arms in the galactic disks, and in the central part we have a spherical structure which we call bulge. And it's a very, very dense structure of stars which are moving around the center of the galaxy. And in the right center we have a supermassive black hole. Supermassive black holes are different from the regular stellar black holes by their history and formation. And around every galaxy, around the disk of the galaxy and bulge, all these structures are actually in the middle of the dark matter halo, which we cannot see, of course, because dark matter very, very weakly interacting with electromagnetic waves. So there is no way to directly observe the dark matter. But how we can detect dark matter? From rotational curves. You said that. Thank you. That's a correct answer. So yeah, dark matter. It feels gravitational attraction, so we can detect by the rotational curves, by measuring velocity dispersions, and of course it is predicted by cosmological models, so we can also measure the amount of dark matter on the large scale, and we know that large scales, and we know that we have about 25–26% of dark matter in the universe. Okay, and this is artistic image of the spiral galaxy. So we have a bulge. This is a spherical object in a spherical area in the center of the galaxy, which consists of the stars, and then we have a disk of stars, and of course in that disk we also have gas, dust, magnetic field, and so on. And we have globular clusters, which sometimes we call it a stellar halo of the galaxy, and all of this is in the dark matter halo galaxy, which is much larger than galactic disk and more massive, about 10 times massive than a visible part. So, do you know why gas is important in galaxies? Why it is important that we have a gas in galaxy? Can we have stars without gas? Because stars are forming by the collapse of the gas. So that gas in the galaxy collapses and forms stars, and that's the reason why we can see galaxies and stars. And can you tell me in which part of the spectrum we can mostly see galaxies? Is it radio spectrum? Is it optical? Is it, I don't know, X-ray? In which part of the spectrum we can see galaxies? In which part of the spectrum they emit the most photons? Maybe radio galaxies in the radio waves, but mostly in the optical part. So, because the most of the visible mass is consisted in stars. About 90% of the visible mass is consisted in stars, and the other part is in the gas and dust. So the stars are the most brightest part of the galaxies, and mostly stars emit most of the photons in the visible part of the spectrum. So the galaxies will also, if they are a collection of the stars, and they will emit the most photons in the visible part, so about 900 nanometers. Okay. So the main properties of the spiral galaxies is that the stars in the disk have almost circular orbits. So this is a pretty nice motion, like planets around the sun. So the stars orbiting around the center of the galaxy. For example, in Milky Way, Sun is orbiting around the center of the Milky Way, and it has one orbit for 220 million years. So in galactic years, Sun is a very young star, about maybe 20 galactic years, 20 galactic orbits. And the disk is dynamically cooled. So we call this, when you have this like a current, like a motion that is not disturbed, we then say that this disk is dynamically cooled. And we also have the small vertical component of the velocity. So all stars are more or less moving in the same plane around the galactic center, and we have those spiral arms that are formed in the galactic disk. And a few years ago, we launched a new mission, Gaia mission, and the main goal is to measure distances, velocities, and later metallicities of the stars in the Milky Way, and it will be a very large sample of stars. And why do we need to measure distances, velocities, and other observational properties of the stars in our galaxy and of the galaxies in general? Why do we need to measure those? Why do we need those data? That data. When you do some research, you need to have some motivation. You need to have some reason why you're doing something. And my question is, okay, we measured in previous missions, we measured some distances, velocities, metallicities of the stars in our galaxy. Why do we need to have a large sample, and why do we need to have these data in the future? Yes?
From data about our galaxies, we can extrapolate about other galaxies.
That's correct. That is one reason, that's correct. And the other one, we need to know, when we have a large sample, we can actually make some dynamical description of the galaxy and try to figure out what was the evolution of the galaxy. And then, as you said, we can extrapolate on other galaxies and try to conclude something about the galactic evolution in general. So that's why we need these data. And also, one more reason is when we have a theoretical research, when we do some theoretical analysis of galactic evolution, morphology, formation, and so on. When we say theoretical, we have some basic theory. For example, mostly in this case, it's only Newtonian gravity when we talk about dynamics, and of course we have some electromagnetic theory when we talk about radiation and so on. But when we talk about gravity, we only assume here Newtonian dynamics. We don't need to go to the general relativity because the velocities are not too high and the time scales are in billion years, so we can describe the gravitation between galaxies and inside the galaxy by the Newtonian gravity. So we have some basic theory, and then when we want to see how that theory runs the galactic evolution, we need to do simulations. So when I say theoretical work, I mean simulations. It can be SPH simulation, it could be n-body simulations, but simulations are actually the basis of the theoretical work. And when we do simulations, we need some parameters. We cannot just put some random numbers in our code, and that parameters we need to find as better as we can. And to do that, we need a large sample of observed data. We need velocities, we need distances, we need as much properties as we can observe and as we can get from the missions, mostly space missions, of course. So this is connection between observation and theory. So I would like that you remember that. And I already said this has a gas, and some spiral galaxies have bar. And when we talk about bulge is more prominent within morphological types closer to S0, so those types that are closer to lenticular galaxies and elliptical galaxies. And it's a mostly spherical shape with chaotic motion of the stars in the bulge. When I said chaotic motions, I mean they have the bulge has a very large velocity dispersion, so we cannot describe bulge with one velocity. For example, you can describe disk with one rotational velocity at some distance, of course, and you can say on this radius stars are moving with that rotational velocity around the center of the galaxy. In this case, we cannot do that because we have a very large dispersion. What does it mean, dispersion? When you draw Gaussian, it will be very broad. So it will be very broad, and you will have the, let's say, similar chance to pick up the stars at any velocity. And when you have a very narrow Gaussian line, you will have a precise higher velocity of picking objects that are moving with the mean velocity. For example, you can imagine like that. Okay, and in the center we have a supermassive black hole. I will tell you something about this evolution and formation of the supermassive black holes. So, how we can measure a mass of this supermassive black hole? You heard one lecture about that. If we have gravitational attraction between two bodies, we can apply Newtonian law of gravity, of course, and what is the consequence? What laws are consequence of the Newtonian law of gravity? Kepler's law, of course. If we measure, if we measure these orbits, I mean periods in these orbits of these S stars in the center of the Milky Way, and from these orbits, all stars are moving around some very, very large mass which we cannot see. And this mass in the middle is actually mass of the supermassive black hole. And by measuring these orbits, we can measure the mass by using Kepler's law, we can measure the mass of the supermassive black hole in the Milky Way. Of course, a few years ago, we detected the surroundings of the supermassive black hole. The first one was in M87 galaxy. It's a large elliptical massive galaxy, and Event Horizon collaboration in 2019 detect these surrounding gas around the black hole, and we call it the shadow of the black hole. And actually, it's a circle which is projection of the let's say last photon sphere. And last photon sphere is the last trajectory, stable trajectory of the photon who is moving around the black hole. So we measure these basis of these objects. So actually, it is a projected last photon sphere, and it's a little bit larger than event horizon of the black hole, and smaller of the accretion disks. And this is comparison between M87 supermassive black hole in M87 galaxy and our galaxy. So you can see that this is the radius. If you put the supermassive black hole for Milky Way galaxy in the center of this image, it will be in this volume. It's much smaller than the supermassive black hole in M87 galaxy. And M87 is very massive elliptical galaxy, more massive than Milky Way, and I think this black hole is 1,000 times more massive than the supermassive black hole in the Milky Way. So it's you see that it's a Pluto's orbit, and this is Mercury's orbit. So it's pretty larger. And this Event Horizon telescope is actually a group of radio telescopes all around the world, and they are working like interferometer, so they can observe in radio waves the signal from the area which is very close to supermassive black holes. Supermassive black hole. When we talk about the formation of the supermassive black hole, it's still an open question. We have several scenarios. For example, when we have a formation of the black hole, you know how black holes are formed. They are, yes?
We have like this object of great mass that actually becomes a black hole. That's it.
Yes, it's a product of stellar evolution. So it's one of the ending stages of stellar evolution. So we have a very massive star. When it collapses, and the central part of the star, if it is more massive than 3 solar masses, it will end like a black hole. And those black holes can have 10, 20, 50 solar masses. For example, the first detected gravitational wave from the black hole mergers, we had 2 black holes which are around 30 solar masses. But these black holes, they have 10 to 9, 10 to 6, or 10 to 5 solar masses. So it's 1 billion solar masses, or 1 million, or 100,000, and so on. So you need to have some different scenario of their formation. And one of the proposed scenarios are direct collapse of a great amount of the gas, because in the beginning of the galactic formation, when we have dark matter halos that attract the baryons in their centers, then we have a large amount of gas, for example, 10 to 5 or 10 to 6 solar masses, and then when it collapses, we don't have any let's say, efficient way for cooling. So if we don't have cooling, all that gas collapses into black hole directly. It skips the part with the stellar evolution. For example, we know that from the molecular clouds, which have I don't know 10 to 5 or 10 to 6 solar masses, we have star formation in them, and around 20% of the star, around 20% of the mass ends in stars, and the rest of the mass, the rest of the clouds is just fly away due to solar winds, stellar winds, let's be precise. So when we don't have that kind of star formation in the clouds and it is packed on a very small volume, we will have direct collapse to the black hole. And of course, after forming black hole, we then have accretion of the surrounding material. Actually, black hole eats all surrounding material and increases its mass, and those are primordial black holes. The other way is that we have primordial black holes that are formed in the Big Bang, after Big Bang. And of course, when we have galaxy mergers, someone asked that a few days ago, when we have galaxy mergers, their supermassive black hole also merged, and they are producing, in that merger event, they're producing gravitational waves. So it's one more way to detect supermassive black hole mergers. So they're important because of the emission of gravitational waves, but of course that is a channel for increasing their own mass. And we have some interesting relation. It's a empirical relation between the mass of the supermassive black hole and velocity dispersion in the bulge. So it's almost in this log scale, it's a straight line. So it's an empirical relation. We still don't have some theoretical background for this, but we can estimate by measuring the velocity dispersion in the bulge, we can estimate the mass of the black hole in the center, supermassive black holes. And now if we move from this baryonic part, from this visible and, let's say, more or less known part of the galaxy, we come to dark matter halo. And we also have these two approaches. One is observational and the other one is theoretical. If we talk about the theoretical approach, Tumra brothers did some n-body simulations in the 70s, in the last century, and they realized that you need to have dark matter halo to achieve this disk stability. If you don't have dark matter halo, disk will just fly away, and it won't be stable on some long time scales. When I say long time scales, I mean more than 1 gigayears. So you won't have a stable disk on galactic time scale without dark matter halo. Later, Vera Rubin was observing a lot of rotational curves in spiral galaxies, and she realized that if you observe some gas which is far away from the galactic disk, I mean on the larger radius, you will have the same velocity, same rotational velocity as in some inner part of the galaxy. But you don't have a mass to support that high velocity. You can, for example, do some very simple exercise, or maybe you already did, how to calculate circular velocity on some radius. Well, you can equalize the gravitational force and centrifugal force, and then to derive the expression for the circular or rotational velocity, it's a square root for g times m over r. And then when you go on larger r, after some radius, you will have a whole mass that you enclosed in your account. And when you enlarge your radius, the r will be more larger and larger, and the mass will be the same. So by the Keplerian law, by the Newtonian gravity and Keplerian law, it should drop off. So this rotational velocity, as r increases, should drop off. But we measure some very high values of these velocities. And after, for example, this radius of 8 or 10 kiloparsecs, we don't have any more stars to contain that mass. We only have, for example, hydrogen, which is in a gas, okay, and the mass of that gas is not large enough to support the value of the rotational velocity. And Fritz Zwicky also measured the velocity dispersions of the galaxies which are on the edge of the galactic clusters. So in the same way, if you want to have a stable galactic cluster, you need to have a satisfied virial theorem. It means that 2 times kinetic energy over potential energy should be equal 1. if you have a higher kinetic energy, then everything will fly away. If you have a higher potential energy, everything will collapse. So you need to have some balance between potential and kinetic energy. And when he measured the velocities on the galaxies on the edge of the cluster, he said, okay, these are too high velocities. They shouldn't be bound into the cluster, but they were bound into the cluster, coma cluster. And he said, okay, we need to have some more mass here, which we cannot see. And he called it dark matter. And this is the story from previous slides. So we are measuring rotational velocity from the stars while we have a disk, and after this we actually measure from 21 centimeters hydrogen line. And then this would be expected from theory that we had before we found dark matter. And this is what we are measuring. So we need to have some mass here to support this high value of rotational velocity, and that mass is dark matter halo. And this is just one more image of the same thing. So you measure, this is your expectation from theory, and this is your measurement. So you cannot see stars here anymore, but you can measure from hydrogen line. By the way, do you know how this line is formed? Does anybody know? You have a proton and an electron in hydrogen, okay? They can be parallel or anti-parallel. And when hydrogen atom changes its state from parallel to anti-parallel, it emits it emits a photon with very low energy on the wavelength of 22 centimeter. It's a famous wavelength, and it's a famous photon. And in which part of the spectrum we can detect this photon? Okay, for sure it's not a visible photon, okay? Because our eyes can see from 400 nanometers to 700 nanometers, so this photon has a large wavelength. It's a radio wave, yeah. It's a radio wave. And it's very important for detecting the structures in the universe at all, because we have expanding of the universe, and we have stretching of these photons of 21 centimeters. So by measuring of the wavelengths, which are now in meters, we can actually measure how universe expanded in the meantime. Okay. And a few words about elliptical galaxies. So they're not so, I will have to hurry up. So they're not so, let's say, interesting like spiral galaxies, because they have almost spherical shapes, and brightness is almost uniformly distributed, and they do not have too much dust, gas, and young stars. And they also spread over large ranges of luminosities and masses. So the most massive galaxies are elliptical galaxies, and they are settled in the center of the galactic clusters. We call it CD galaxies, or core dominant galaxies. They have 10 to 13 solar masses. And when I said the whole mass of the galaxy, I mean the both part, baryonic part and dark matter halo. So the 90% of the mass in these galaxies are contained in dark matter halo, and the 10% in this baryonic part, this part that we can see. And they're mostly formed in merger events. Why it is important? Because, okay, this is the picture of one elliptical galaxy, and we have some spiral galaxy behind. They are mostly formed in merger events because we will see that large massive galaxies are formed in mergers of galaxies with a smaller mass. That is one thing, and the other thing, these galaxies can also be formed in the mergers of the spiral galaxies. Then disks usually get destroyed, and then we have these galaxies also with large velocity dispersions and spherical shapes. Okay, and we also have some empirical relations for disk and elliptical galaxy, for example, some relation that connects velocity dispersion and magnitude. It's a Fabre-Jackson relation for elliptical galaxies, and we also have this relation which connects the velocity, rotational velocity and absolute magnitude for spiral galaxies, which is Tully-Fisher relation. And I'll just briefly mention the active galactic nuclei. We can see, for example, you already heard about, I suppose that you heard about radio galaxy, about blazars, quasars, and so on. We have a unique model for all these galaxies, and we have differences between galaxies. It depends under which angle we are observing this galaxy. And when we count the number of these galaxies through the history of the universe, and this is redshift, so it's a measure of the time. Let's say it's a measure, or it's a time measure. So higher redshift, that means deeper in the past, okay? So if we measure the number of these active galaxies, we can see that we have some peak here around Z equal 2. So we can conclude that maybe the active galaxies are actually the one stage in the evolution of the galaxies. And what does it mean, active galaxies? We have supermassive black hole, we have jets, we have accretion disk, and this torus of dust. And this part is very, very bright, and it's more brighter than the rest of the galaxy. So they got named quasars, like quasi-stellar objects, because they look like stars, but they're not stars. So we have a whole galaxy surrounding this, but this is so bright that we cannot see the rest of the galaxy. And it's probably that these galaxies are the part, just one stage in the evolution of the galaxies. And we have dwarf galaxies. So when we talk about dwarf galaxies, we also have some different morphological types, like dwarf spheroidals, ellipticals, spirals, compact, ultra-compact dwarf galaxy, and so on. And these galaxies are very important because in the first stage of the universe, they survived the merger events. So there are some ancient galaxies from the early universe, and today they're mostly satellites of the larger galaxies. Okay, I will speed up this. When we talk about interactions of the galaxy, do you know which galaxies these are? What are these galaxies? It's our satellite of the Milky Way. They're in the halo of the Milky Way. You can see it from the south. Okay, those are irregular galaxies, but do you know the names of these two galaxies? Yeah. I think you said correctly, yeah. It's a Magellanic Clouds, yeah. That's correct answer. So these two galaxies are Magellanic Clouds. They are irregular galaxies. They are inside of the halo of the Milky Way. So they are surrounding center of the Milky Way, and they are actually moving around the center of the Milky Way, and they feel some tidal disruption in the halo of the Milky Way. So Milky Way is actually eating these galaxies, so they have some irregular shapes. And we also believe that some globular clusters on the high latitudes in the Milky Way are also remnant of the satellites of the Milky Way. Okay, when we talk about interactions, we have several types of interactions: mergers, flybys, tidal stripping, and so on. So these, for example, these galaxies, because of the gravitational attraction, they also have some tidal interaction, like a moon and the Earth. You heard about tides. And the same thing is happening in galaxies, but galaxy is not one body, it's a system of bodies, and then these stars and gas which are more closer to this galaxy are starting to be pulled by this galaxy, and then we have formation of these streams, bridges, shells, and so on. Okay, this is PDF, I forgot, okay. I can show you some short movies about. This is the merger event between Andromeda galaxy and its satellite, which forms some stellar streams and shells, which we now can observe in halo of the Andromeda. I will show you in the movie when I finish the presentation. And this is also one hydrodynamical simulation. I will show it later. Now, a little bit equations. When you talk about how we model these merger events and how we model galaxies. This is maybe a little bit too rough, but I think it's pretty simple. We need to obey several principles, several laws. For example, the total energy in the simulation has to be conserved, and this is the sum of the potential energy and kinetic energy of each object. So if we have n object, we're just summing from 1 to n. This is the moving of the center of the mass. Angular momentum has to be conserved, so this is just a cross product of the position and velocities, and the distribution over positions and velocities should also be conserved, and this is Boltzmann equation, collisionless Boltzmann equation. So we suppose that we don't have any collisions between stars. It's a very rare situation, but when you talk about mergers of the galaxy, it's a very common. But collision of the stars in the galaxy is very, very rare. And if you calculate the mean time between two collisions, it will be larger than the age of the universe. So the probability to have collisions of the stars in the galaxy is very, very low. So this function, which is distribution over distances and velocities, should be conserved. That means that we have the same density profile of each component of the galaxy. This is, okay, this forget, because probably you don't know this symbol here. It's kind of derivative. It connects galactic potential and the density, and this is a virial theorem. So the T means kinetic energy, omega is potential energy. So this is the same equation. We need to have this satisfied if we want to have a stable system when we are modeling galaxy. And of course, we need to calculate, and in numerical simulation, it is good included, dynamical friction. For example, you know what is the friction in the motion. If I'm going on this stage, thanks to the friction, I can go normally, of course. And but if I put this pointer here, thanks to the friction, it will slow down. The similar thing, but in dynamical sense, is happening in galaxies. So we have if we have a merger of the galaxies, and these more massive objects actually pulls these less massive objects. But these objects, their collective mass acts like a friction on this body, and it slows it down. You slow it down, okay? And the last chapter, formation of the galaxies. So, what you can see here. Yeah, I'm not sure it's a galaxy cluster, it's just a part of the sky. It is observed by the Hubble telescope. It's a famous Hubble Deep Field. And you can see what is the dominant color on the image. Orange, okay, maybe. And blue, okay. But the most pixels do not have any color, they are black, okay? So the space between galaxies are mostly empty. And if we talk about homogeneous and isotropic universe, which is a cosmological principle, we can say, okay, if we have a homogeneous and isotropic universe, why do we have black dots on this image? And the reason is, we also heard about that in previous lectures, the reason is because the universe has some finite age, so it's not, it doesn't have infinity. It's not infinite, that's one thing, and it has a finite age, and it's old. How much is old? Around 14 billion years. 13.8, 13.9. Okay, so when we talk about galaxies and clusters of the galaxies, we are actually counting galaxies on the large scales, and we try to see what we can learn from the large scales. And on the large scales, so if we zoom out enough, we can see that universe is homogeneous and isotropic. And also, thanks to the density fluctuations in the early universe, so we have these let's say, almost homogeneous universe, and we have some small fluctuations in the early stage of the universe. We will have formation of the structures. First of all, we will have we will have fluctuations in density, and then we have formation of the structures of the dark matter halos, then which attract baryons, and then we have formation of the galaxies. So how we can trace these density fluctuations? Maybe you heard about baryonic acoustic oscillation, but I will skip that part. We can trace it by fluctuations in the temperature. For example, this is the picture of the whole sky. And these colors represent different temperatures, but they differ from minus 200 microkelvins to plus 200 microkelvins. So if we are measuring temperature on 2 decimals, it will be the same color. All sky will be the same color. And do you know what entity we are measuring temperature here? So this is temperature of what? Louder? But what is that exactly? Are there stars, galaxies, or some photons? It's a cosmic microwave background. So these are photons that are emitted in the very early stage of the universe after, let's say, approximately 400 years after Big Bang, and they are decoupled from the matter, and they are actually in thermodynamical equilibrium. And those photons at that time had temperature of 3,000 kelvins. Now they have temperature 2.73 kelvins. And when someone asks you what is the temperature of the universe, you will say 2.73 kelvins. So it's a pretty low temperature. And it is, those photons are all around us, so it's the first photons in the universe. And we have several missions who measured this temperature. COBE, Cosmic Microwave Background, WMAP, and Planck from 2015. And this is the same map like the previous one. Do you know what is this part here? It's a Milky Way disk, so it omits us to measure other temperature, temperature behind that, and we need to interpolate those temperatures. Why this is important? Because this is the true black body in the nature. Black body is a model. When we talk about how stars emit their lights, we say, okay, the spectrum of the star is actually the same as the spectrum of the black body. But that's just approximation, okay? This is not approximation. When we measure, this line is a theoretical prediction, okay? It's a Planck's law, okay? And these dots with error bars are measured brightness on the different wavelengths. And this line corresponds to the temperature of 2.73 kelvins. And you see these error bars are multiplied by the 400. This is the measurements with the most precision in the history of science, I think. So it's very important. Why we have this law? Because in that time, in the early universe, we had actually the thermodynamic equilibrium between matter and radiation. And when they decoupled, that first photon, they stood in the thermodynamic equilibrium in that part of the cosmic history. And then after that, what we had expansion of the universe. We had stretching of these photons. When they increase their wavelengths, they're losing energy, because if we have larger wavelengths, we have lower energy. Do you agree? So if they had 3,000 kelvins in the beginning, when they decoupled from the matter, now they have almost 3 kelvins, so 1,000 times less. And just for comparison, this is the spectrum of the sun. This is measured spectrum of the sun, and this is theoretical curve. So it's pretty different from this thing, okay? So sun is just approximately black body, not whole sun, but that part from which we get the spectrum, okay? That surface part which we call photosphere, okay? And this is the resolution, evolution of the resolution on these missions. COBE was launched in 1990, I think, WMAP at the end of the 90s, and Planck in 2000s. Why do we need to measure these fluctuations? Because if you see on 2 decimals, everything is the same. But because from these temperature fluctuations, if you remember 2 slides ago, from these temperature fluctuations we can measure density fluctuations and how the structures on the large scales are formed. That's why this is important. And also we can measure the parameters in the universe, like how much do we have dark energy, dark matter, visible matter, and photons, and so on. So I will skip this part because you already heard that the universe is expanding. Hubble measured it in the 20s of the last century. So if a galaxy is further away, it will go from us with a higher velocity. This recessional velocity, and this is not because they are moving in the space, but because the space itself is expanding, so the physical distance is getting large, and the coordinate distance is the same. You can see it on these balloons. So if we put some coordinate system, you see these coordinates 0, 0, 1, 0, 0, 0, 1, 0. So the coordinate distance is the same, but the whole system is expanding. Whole coordinate system is expanding. So the physical distance is getting larger. And what do we know else? The connection between physical true distance and this coordinate distance, we call it scale factor. And scale factor of the universe is connected with the density of the universe and so on. These parameters we can measure from cosmological measurements. And from those cosmological measurements we can measure how much, because these missions are actually giving us parameters of the universe on the large scales. And these are several tests, supernova type 1a, and we concluded, thanks to them, that the universe is expanding with some acceleration, so we have accelerated expansion. We have a cosmic microwave background. This is that CMB that I mentioned before, and these baryonic acoustic oscillations. And all these scenarios are intercepted in this area, which had parameters that we have omega lambda, that is ratio between, omega lambda is ratio between density of dark energy and critical density, okay? And omega m is ratio between density of matter, I mean baryonic matter plus dark matter over critical density. So we have about 30% dark matter plus baryonic matter, and around 70% or 0.7 for omega lambda for dark energy. Okay? So, and this critical density, when you said omega is a ratio of the density, this critical density is connected to Hubble constant and Hubble constant over Hubble parameter. It is better to say Hubble parameter, and Hubble parameter is connected with the scale factor. And you remember from previous slide, scale factor is actually connection between physical distance and coordinate distance. And now, if we talk about the evolution of the universe in this manner, we need to include general relativity. And the theoretical solutions of equations with general relativity were given by Friedman and Lemaitre. So we also have this theoretical approach and observational approach. And this is the history of the universe. You already saw this image. So we have decoupling of, let's say, decoupling of here, decoupling of matter and radiation, and then structure formation, and this space is also filled with cosmic microwave photons. And from just one more image from this homogeneous universe, we have small fluctuations which lead to formation of the galactic clusters. So just 2 slides to finish. First of all, we have a top-down model of gravitational collapse, and that means that each part of the galaxy is formed at the same time, and we know that it is not true from observations. So now we have this bottom-up or hierarchical model. So we have first formation of the small galaxies, and then they merge to construct the large massive galaxies. And So we have a formation of the bubbles of the dark matter halo, which attracts baryons and form galaxies. And these surviving galaxies are dwarf galaxies. And all of these structure formation is in between these 2 points. So we have several era in the history of the universe. We have radiation dominated era, we have matter dominated era, and now we have, you see this rho cc as actually density, energy density of the dark energy. So it is more or less constant, and all of the other densities drops off. So now we have, at this point, we have domination of the dark energy, and before that we had the structure formation in the era where matter was dominated. So when you talk about galaxies, I will skip some of these things because I already mentioned. We have hierarchical growth of structures of galaxies. First of all, we have halo formation in dark matter collapse, and then we have attraction of the baryons. We have galaxy formation. Those are small mass galaxies. They merge, they form large massive galaxies, and then today we can see the various morphological types of galaxies. So, and when we are investigating galaxies and universe, we are actually working with building blocks of the universe. And we do that with this comparison between theory or simulations and observations. That's why we need to have a large computers, but we need to have large telescopes. And I will finish with this. Those are some references with some general books or books that are dedicated to galactic dynamics. So you have one very interesting book which is free and it's online, and I can share this presentation so you can visit this literature when you come home. Okay, thank you. And just one question for the end. Do you know what is the difference between these two pictures, these two images? Yes? Okay, which one? Yeah, it's, the left one is Hubble, and this is the same area observed by James Webb. And you can see some lensing here, okay? You can see some lensing here, probably due to the dark matter, which we cannot see, of course. Okay, thank you. I will finish with this, and I'll also have some slides with some theoretical work of our high school students from Petnica Science Center. They, for example, this one is interesting because this guy made the n-body simulation to describe the polar ring galaxy, and this guy made simulation to describe formation of the antenna galaxies in the merger event of two galaxies. So these are true images, okay, and these are simulated. And this is also simulation which try to find the conditions for bar forming, and if we have these A2 parameters over 0.2, we will have formed bar in this galaxy. So obviously we have formed bar. This is just a short commercial about what high school students can do. So I'm inviting you to start to do science as soon as possible. Thank you.
Thank you very much, Professor Stanislav Milosevic. I think we have time for a couple of questions.
Okay. Yes?
How can you tell apart how can you tell apart cosmic background radiation from other types of photon emissions in order to measure the temperature of these photons?
That's an excellent question, because it is the only radiation on that temperature. It is very low temperature, so it's just 2 degrees above the absolute zero. That is one thing. The other thing is the same properties of that radiation on each scale of the universe. So if you observe at any direction, you will see the same properties of that radiation. For example, when it was discovered in 1965 by Penzias and Wilson, they thought that they have some pigeons in the radio telescope. and that they're making some noise. They thought it's a kind of noise, but then they realize, and thanks to theoretical work by Peebles and others, that it's actually cosmic background radiation. Those are first photons, and they are in the equilibrium, thermodynamic equilibrium with themselves, then that opened the other question. Why do we have the same properties of that radiation on such large distances? Because if we took two dots on the separate part of the sky, and if we calculate, were they in some kind of communication in the history? If we do not have inflation in the early universe, they wouldn't have enough time to communicate and to travel on so large distances. So it's this radiation has very specific property of the thermodynamic equilibrium. So it's the only true black body in the universe. So if you find that photons, you will not miss it. So that will be the CMB photons.
Thank you.
Thank you. One last question, please. You.
Do we know which is the shape of the universe?
Which is?
The shape is spherical, which is flat, which is the shape?
Yeah, that is also a good question. I think on the first day we were talking about that in the first or second lecture. We believe that now it's a flat universe, so the parameters are giving us, observed parameters are giving us that conclusion. So it's actually kind of flat universe. When we calculate from Friedman equations, we have three classes of solutions. We have one solution with parameter that can give us open, closed, or flat universe, and we have a flat universe. That observation suggests us.
Okay, thank you very much. Now we're going to take a short break, 10 minutes break, just to take some fresh air, and we'll be back.
Thank you.
Αν και δεν θα έχω ρόλο. Δεν έχω ήχο.
Δεν έχεις παρουσίαση.
Δεν έχω ήχο.
Το βρήκατε ότι θέλετε και στο σχολείο. Θέλετε να κάνουμε κάποιο ραντεβού τηλεφωνικό.
Έχουμε καλή σχέση.
Θες να το μιλήσουμε στη για κάποιο θέμα. Πες μου ποιο είναι το θέμα, να το μιλήσουμε. Εκτός του αισθάνομαι.
Όλα ανοιχτά. Εντάξει, θα το κάνω εγώ. Αυτό τι είναι, εδώ.
Μπορείτε να ετοιμάσετε νωρίτερα, γιατί χρειάζεται και προστασία κάποιοι κάτω. Θα βοηθήσουμε περισσότερο για αυτό. Το οποίο να το διασπάσεις, χρειάζεται περισσότερη ενέργεια. Σίγουρα και κάποιους είδατε το βράδυ που κάνετε πόδους στο δωμάτιο. Να ξεκινήσουμε. Κάποιες κυρίες κάνουν βόλτα. Δεν πάει κάποιο να βόλτα. Grazie.
So I think we can start. So we will continue the exploration of the universe. I think the previous presentation offered me a number of issues that can build on and try to demonstrate and present how important it is really to look for other, I would say, carriers of the messages from the birth of the universe. For example, you have heard that the light, the photons, was decoupled from mass about 400,000 years after the Big Bang. So we are not able, as we said, from the first day to look further, closer to the Big Bang. There is a particle, or a family of particles, in principle, it's not only one, where these were decoupled from the matter much earlier, immediately after the Big Bang. So these particles have specific characteristics. Really, they have amazing characteristics. And maybe they are very useful to act as carriers for the information we are looking for. So these are the neutrinos. And I have added in parentheses a title that usually we are presenting this issue, fishing for neutrinos. And I'm going to explain to you why we are fishing, in principle, for neutrinos. During the presentation, my colleague and collaborator for many years at the Nestor experiment. The Nestor experiment was a major effort, a Greek, Russian, French, Italian, German cooperation that have tried to install one of the first neutrino telescopes in the Mediterranean Sea. So we will have the chance to present together some of the issues, and of course later in the lab, in one of the two labs, we will further emphasize on the detection technique and the phenomenon that is used to help us to see the messages from neutrinos. As I told you, all of our efforts here in this course, in this summer school, is to introduce quite complex topics related to recent Nobel Prizes. And in 2015, the Nobel Prize was awarded to these two scientists who have coordinated two very big experiments underground, looking for neutrinos, and more specifically, looking for the oscillations of neutrinos. This is something very strange. What can be an oscillation of a particle? What is an oscillation of a particle? But this is exactly what we are going to discuss. The discovery of neutrino oscillations that demonstrate that neutrinos have mass. In fact, at this moment, with all this work that we have done, we still don't know the exact mass of the neutrino. We have just set some limits, and we are able to know that they have mass because we are able to see this phenomenon, the oscillations of neutrinos, the change, let's say, of the particle from one member of the family to another while they are crossing the matter. And in this way, we estimate the difference between the masses of the different, let's say, relatives in this family. But this is still a very big problem. I would like to say that, of course, is not a term that scientists are using, but for a very big number of reasons, we have given a name to neutrino that scientists usually, as I said, are not using, but it's really a challenge to work with this particle, so we call it the ghost particle. And in fact, maybe you know that it was related already some years ago with the issue and the question if there are particles that are moving faster than the photon. And there were at least 2 cases in the recent scientific history where this discussion came forth. So it is always entering in the discussion the relation between the mass of this particle and its specific characteristics. But let's go a bit back, about 100 years, 4th of December 1930. By the way, this is the translated in English, the letter of Pauli. You can find it to the Pauli archive at CERN, and you can read also the original that was written in German at that time. It's a letter that Pauli is sending to his colleagues because he will not be able to attend a major conference, but he's sharing with them his initial ideas about the specific characteristics and the data that they are getting for the beta decay. Beta decay, they were facing a number of problems with beta decay, as they were missing some energy, because there are some important, let's say, laws in nature that we believe that apply everywhere. One of them is the conservation of energy. Okay? The other one is the conservation of momentum. So these are major laws. So when something seems to violate them, of course we are surprised, and we are looking either where we are making the mistake or what is the new component that we have to add in order to solve this problem and this equation. So he's saying that, let me take the graph. So he's saying that I have an idea, in principle, that will help us to keep our ideas about the conservation of energy. So he says that I believe that there is an additional particle appearing during the beta decay. It has no charge, and he is calling it neutron. He says that it has spin 1/2 and obey the same principle, and its main difference, let's say, with the light is that he is not traveling with the speed of light. So he's using the term neutron. The neutron was not discovered at that time yet. It will be discovered 2 years later. In fact, he is too skeptical about for this proposal. He's not really sure, so he's not publishing it. So when Enrico Fermi, a major physicist from Rome, from Italy, about 2 years later, and when the neutron has been discovered, and of course, Fermi was studying also the beta decay, and he had specific ideas about that. He's getting a question in a conference if neutron is the particle that Pauli was talking about in beta decay. He's saying, no, it's not the same. The particle that is appearing in the beta decay is much, much smaller. So instead of neutron, is giving the name neutrino, so a small neutron, neutrino. So in principle, Enrico Fermi became the godfather of this particle, although 2 years earlier, 4 years in practice, earlier, Pauli has announced that in this letter. So this is a bit even demonstrating the complex character of neutrino. This is how it came up to the scientific landscape. So about 40 years later, we have the first neutrino event. This is taking place in a bubble chamber. So exactly as we see in the sky, the track of an aeroplane, maybe the aeroplane is very, very far and we are not able to see it, but we see the line that is creating in the sky. In the same way, we can see the tracks of the particles. And here we see a strange phenomenon. As we said, one of the most important laws in physics, in nature, is the conservation of momentum. So what we see here we see a particle here, another particle there, making a big track, and another one here. Okay? Do you think that the momentum is conserved in this graph? Could it be? Do you understand the question? No? Okay. This line represents the track of a particle. This is another one, and this is another one. So something happened, and 3 particles appear in the graph. Something happened there. What was that? Yes? A collision. Okay. Which are the particles that collide? I need, in order to have a collision, I need a particle to come, for example, from here. I have another particle here, maybe it's not moving. So one particle is coming, hitting this particle, and then they are moving to different directions. A neutrino and a neutron. Okay, let's change a bit the question. I have a particle, the momentum of this particle is about here, of this particle there, and of this particle there. They are moving all of them to this direction. What is the overall momentum of the 3 particles? What is the direction of momentum of the 3 particles? Yes? Yeah, a middle, let's say a line somewhere here, correct? It must be an arrow at about here. So this is after the collision. I need the momentum before the collision. It has to be the same. The collision, the momentum before and after the collision they have to be the same. So there must be a particle here. This is what these data are saying, because these are real data, that there is a particle that is coming from here with exactly the same momentum as the resulting one. Okay? And I'm not able to see it. It's invisible. It's invisible. We are not able to see it. That's why we call it ghost particle, because we are not able to see it. There is a neutrino here coming, collides with a proton in the chamber, and the heavy proton is moving a bit, is making a small track. There is this muon created, and a pi meson also here. So this is the first, let's say, observation, if we can say. Observation, you remember in the first presentation 2 days ago, I was discussing about the Higgs boson, and I told you also that we are not able to see the Higgs boson. We see only the result of its appearance. So it's similar here. I'm not able to see the neutrino, but I can see the result of its interaction with matter. So Enrico Fermi, at that time he has a very good group of young scientists in his lab in Via Panisperna in Rome. And these are, they are called the boys of Via Panisperna. In fact, most of them were involved with Fermi later to the project about the development of they moved to the States, and they work for the development of the atomic bomb. One of them, he worked a lot on the mass of the neutrino, was Ettore Majorana. There is a book I will really recommend to you. It is called Brilliant Darkness, and in principle the book is presenting its life, because Ettore Majorana just disappeared. He was traveling from Naples to Sicily on a ship, and he disappeared. His body was never found. There was no information about him. For the Greek students, the book has been translated in Greek, and is called The Neutrino Man, or Anthropos Neutrino. He disappeared like the neutrino. The other guy below is the only guy who had different views about the world from the other boys of Panisperna. So he was a communist, and he decided, when everybody left and they went to the States, he continued his research in Moscow at that time, and he is also very, very important. I will come to his work later, because his work is really directly connected with the oscillations of neutrinos. He was really introduced the oscillations of neutrinos, and he was also able to solve the standard model, the sun standard model problem, as we will discuss. His name was Bruno Pontecorvo. So these are the key characters in the story. Now this is the beta decay, as I mentioned, the nucleus of their splitting, and they are producing. Do you know what this symbol shows? What is this? It is Yes. Yes. Electron. Okay, and this? A positron. Okay, is the antiparticle of the electron. Perfect. This is the additional particle. It's an electron neutrino. I said that the neutrinos are forming a family. I will discuss about that in a few minutes. So these are the electron. This is an electron neutrino, while this is, what is this line on the top? Do you know? Anybody? Is the antiparticle of the electron neutrino. Okay, this is how we mark this. We are not able to present a positive or a negative signal because it's neutral. So we characterize this particle with this line on the top. This is the antiparticle. Okay. Eleftheria Sotiriou presented on the first day the sun and how sun is working. So if we want to present a detailed model of the sun, of all the processes, all the chemical processes in the center of the sun, this is what we have to present. So this is how sun works. Okay? It has all these chemical interactions where I have identified where neutrinos are coming. Here we have neutrinos. Here in this interaction we have neutrinos. Neutrinos, neutrinos. So one of the most rich, let's say, sources of neutrinos for us is our sun. So immediately, let's say, when we had the chance to study, let's say, the nature of neutrino, we said, okay, let's collect neutrinos from sun. The sun has is sending us numerous neutrinos continuously, so we have the chance to use the sun as our source and make measurements. And the scientists, in order to study the neutrinos are interacting, their interactions with the matter are very rare, so they had to make, to construct quite complex detectors. They had to go deep underground to use the rock above them as a shield and offer the opportunity to these neutrinos to cross the mountain, the ground above the mine, and enter to the cavity and interact there in order to give their signal. So a number of such detectors were installed in Russia, in Japan, and in other countries, trying to measure the flux of neutrinos, from sun. And a major problem came up. That was a major scientific issue for many years. The problem was that the flux, we believe that we had a very good model of sun. We were understanding how sun is operating, so we had a very good theoretical basis for this calculation. And what happened? All the experiments presented fluxes that were considered lower than the expected ones. So either the model we had for the sun was wrong, or something was happening with neutrinos while they were traveling from sun to Earth, to the detector. Okay? And this was a major problem for this period. And this guy, I saw his picture when he was a bit younger, working with Fermi in Rome. Bruno Pontecorvo said that both the model that we have for the sun and the measurements are correct. Both of them. There is no problem. In fact, he produced, he created really a formula for that, but also he had the idea that the neutrino, in principle, is not only one. There are 3 neutrinos that changing, I would say, if I can say, costumes from time to time. Once I have an electron neutrino, once I have a muon neutrino, once I have a tau neutrino. So these are the relatives in the leptons family. The leptons are electrons, muons, and taus, and their cousins are the neutrino electrons, the muon neutrinos, and the tau neutrinos. And he said that the neutrino, an electron neutrino, can leave the sun, but when it is really crossing the mass, it can change its costume, and it will appear as a muon neutrino later. Okay? And he said that the possibility that I have for changing from neutrino X to neutrino Y is related to the difference of the square mass of the different neutrino types. Okay? This was his major contribution. Okay? This was the theoretical idea that was presented by Bruno Pontecorvo, and it was, I would say, experimentally proven back in 2015 when the Nobel Prize was awarded for the neutrino, for the detection of neutrino oscillations. So another parameter I would like to say here is that this is also related to the length. This is the length of the track of the neutrino inside the mass. So when the neutrinos are in the vacuum, when they are traveling and there is no mass, they are not changing their character. This is happening only when they are crossing the mass. So if they are crossing the mass, we will have to observe neutrino oscillations. So in this idea was really supporting the findings from the experiments, because while the electron neutrinos left from the sun, while they were crossing all the mass that there is between the place of their creation till the detector, the mass of the sun and the mass of the earth, they had the chance to change their costume. So if the detector we have installed inside the mine was ready to observe electron neutrinos, it was observing only the electron neutrinos that survived after this oscillation, that they remain after these oscillations. The others were other types of neutrinos that the detectors were not able to detect. And when we were able to construct detectors that are able to detect all the varieties of neutrinos, we found that it's really the sun is working in the specific way, and the neutrino oscillations are really happening. Manolis, would you like to add something here? Maybe about the snow detector?
I would like to ask our friends here.
Okay, so I would like to ask you, why would one choose neutrinos as particles to do astronomy, based on what you have learned so far? What is your opinion?
Mainly for two reasons. First of all, because, as you mentioned earlier, they were created in a very early stage of the universe, and therefore they can provide data even before photons were released. The second reason is because they can cross matter, and this way there are less obstructions in their path to the telescopes, and maybe this way we can get more data.
Anyone who would like to add something? Okay, so as Dr. Soteriou said, neutrinos very rarely interact with matter, and this is a curse, let's say, somehow, if you want to be able to detect them, to observe them, to measure their properties. But on the other hand, it is a blessing, because this way you have a great advantage over the photon. Photon is the carrier of information with which we observe the universe. When you went to the observatory in University of Thessaloniki, you observed Saturn, correct? Wake up. Okay, so now I would like to ask you this. Raise your left hand. Left. Okay, and now try to block the light coming into your eyes from the top of you. Okay, why does this happen? Why do you not see the light anymore? Hello.
Because I covered the light with my hand, and I can't see the light.
Can you explain a bit in the framework of photons coming from there towards you?
It's going to my hand,
Yes?
and not to me.
Okay. Someone would like to ask something?
Our hand absorbs the photons of the light, and for this reason, the light cannot reach our eyes.
So, what would happen if this lamp emitted neutrinos instead of photons? You.
We would never be able to block it.
Perfect. Would you be able to see that?
No, we can never see neutrinos with the naked eye.
So, in order to be able to measure the properties of neutrinos, you need to have them interact somehow. You need to have a very big flux of neutrinos coming from somewhere, usually from nuclear interactions, as you saw, for the example of the sun. And then you need to have a very big detector, a very big, let's say, pool of water, which has trillions of trillions of trillions water molecules, let's say, and you hope that out of the hundreds, thousands of neutrinos coming every minute from the sun, let's say, you may be able to have one interact. See the problem here? Very difficult. So in order to be able not only to detect neutrinos, but also to measure the oscillations and other very important phenomena, as you saw, and you will see later, you need to have very, very big caverns, big places, filled with water, for example, and hopefully one of the neutrinos that is coming your way will interact there, one or more. But you need to protect your detector from all other outside influences, all other outside particles. Photons, you need to block them. No light from outside should get inside your detector. Muons, cosmic rays, which are abundant on the surface of the Earth. So, Dr. Soteriou, you have Kamiokande there, I saw. So you will see the first neutrinography here of the sun. I leave it to you.
Yeah, this is, let's say, another Nobel Prize awarded back in 2002 this is a neutrino image of the sun. Okay, so this is what also we said from the first day. If we were able to see neutrinos, the rain of neutrinos, the storm of neutrinos that currently is taking place between us, I will not be able to see you because of this rain. So you can see that 100,000 billion of neutrinos pass your body every second. Okay, so as we said, you start understanding our concept here. We are start making some small steps. We create images of the sun with neutrinos. Then we would like to create a whole map of the sky with the sources of neutrinos. And for this reason, especially to measure the oscillations of neutrinos and calculate exactly the differences, here we have the possibility to measure the differences between the square mass of the two types of neutrinos. This is the oscillation. We have constructed this kind of detectors. These detectors are located in mines, so they are far underground. This is in Japan, and here you can see the entrance of the mine. There is a very big cavern filled in with water, and the neutrinos that are coming from the sun are interacting here. They are producing electrons, and the light of the electrons is being detected, and in this kind we can calculate their fluxes. These are more advanced detectors, also, as we said, focusing on the detection of the other kinds of neutrino. But this is another thing with neutrino astronomy, because in astronomy I have to be able to find exactly the target in the deep sky. I have to locate the source, and this is very important. As Manoli said, this is also an additional and a very important reason for doing astronomy with neutrinos, because they are not going to deviate. They don't have any charge, so their track will not change. We will be able to go back to the original source if we are able to reconstruct their direction. So, 1987, I have started my first presentation with this supernova explosion at the Large Magellanic Cloud, a satellite galaxy of Milky Way at 168,000 light years away, was observed in Australia on February 23, 1987. It was the first time that neutrinos enter also in the discussion about their speed. In fact, the detectors that were installed to detect neutrinos from the sun, and they had a flux, let's say, of observing 1 or 2 events, neutrinos per day. In a few moments, they are detecting 12, the other 5, and so on, in a burst lasting less than 30 seconds. So there was a rain of neutrinos, a very big flux of neutrinos that they have crossed the planet. All the experiments that were installed for other purposes, suddenly they give very high signals of neutrinos. So where these neutrinos are coming from? At the same time, at the other part of the hemisphere, as we said, at the southern hemisphere in Australia, the astronomers are observing this explosion, this supernova. And the two events are somehow combined, and it's the first time that we are going back and we say that we have detected neutrinos from a supernova explosion. And this is the birth, I would say, of neutrino astronomy. In fact, the neutrinos come faster than the light. And it was the first time that we have discussed that maybe neutrinos are traveling faster than light. But this was not the case. This is because of the process. In the process, the neutrinos are leaving the dying star first, and the light follows. So, in principle, the neutrinos have not were not so fast as expected at that time. Okay, so this is the supernova, and here is a later picture of how things are further developing with the dust of the star moving away. So Manoli said about that before. We have some cataclysmic phenomena, of course, in the sky. They are producing. There is a significant production of neutrinos in this kind of events, and while the other carriers of information are failing to arrive to Earth, neutrinos are the ones that can bring us this information from this kind of events. So they are traveling in a straight line. Nothing can stop them. They are crossing the mass like the light is crossing the glass. And in this way, we can see further away. Furthermore, as we said, they were separated from matter much earlier, in the beginning at the birth of the universe. So if we are able to locate, as the first photons are still around here, as we heard in the previous presentation, these relic neutrinos are also around us. So if we are able to find them, to detect them, then we will be able to get information from the Big Bang. So for this reason, we have to create much bigger detectors, because we need to increase the effective volume of the detectors. The space that we have in the mines is not enough. And if we go in the mine and construct such big detectors, then the whole mountain will collapse. Okay? We are not able to open such big holes in the mountains. So the only place we can go is in the sea. And we have to go very deep in the sea. I mean, as we said, we have to create a shield from the cosmic rays. If there is light, we will not be able to detect neutrinos. If there are a lot of cosmic rays, we will not be able to detect neutrinos. So we have to isolate the detector, and we have to go very deep in the ocean water. So this picture explains, let's say, the title I have used in parentheses, why we say that we are fishing for neutrinos. This is fishing, and this is ice fishing for neutrinos. Let's see how a neutrino detector works. Here is a high energy neutrino. You remember the first graph with the first event from 1970. the picture I have shown. So this is invisible. Here is the proton. It's interacting with proton inside the Earth, and then is producing a high energy muon. Okay? It's exactly the same. Let me go back to remind you this. So the neutrino is coming from this direction and is producing this muon. This muon is growing very fast. And the higher the energy of neutrino, the higher the energy of the muon. This muon can travel for 4 or 5 kilometers before it consumes all its energy. And it's offering us a very good candidate here to reconstruct the track. Because if we reconstruct the track of the muon, it's about the same with the track of neutrino, so we will be able to target back to the source of this neutrino. Okay? So this muon is entering the seawater here and is producing this very faint blue light. Why? Because the muon is moving at about 80% of the speed of light, while in the seawater the speed of light drops significantly. In principle, is divided by the refraction index of the medium. So this is the reason why we have the creation of Cherenkov radiation. This blue light that it is emitted from the track of the muon. The fact is that it has very, very specific geometrical characteristics. So the light is emitted at 42 degrees. So it's offering us the opportunity to reconstruct in detail the track of the muon. Of course, we have to be able to observe this light 5,000 meters underwater in the deep ocean. And this is not an easy task. In theory, we can say we can do it. But in practice, it's much more difficult. Is it clear to everyone? No? Yes.
Can you hear me? Okay, so when we want to detect neutrinos, where do we look, up or down? Down. Why?
Because they travel through the air, because they travel through masses, and through the air, so they come from the ground from the other side of Earth.
Very well. So, similarly, when you saw the neutrinography of the sun, you saw the sun in light of neutrinos. You saw it before, right? Were we observing the sun during day or during night? No, both. During both day and night. Okay? So, with neutrino telescopes, you can observe the sun 24/7. Okay? That was the...
So, the muon is here, is interacting with the matter, is producing the muon, and the blue light is traveling across the track of the muon, and we have to set there a number of detectors in order to see this blue light. Okay? I have to install these detectors in the deep ocean. So how this can be done is exactly what we are going to discuss now. These are the eyes of the telescope. So you understand it's a completely different telescope from what we have seen at the Aristotle University. I will explain this, but here, in this case, I would like to say that it has to be in a sphere, in a glass sphere, that is able to stand up to 500 atmospheres of pressure, okay? Because when I'm going every 10 meters that I'm going deeper, the pressure is increased, okay? At 5,000 meters, I have about 500 atmospheres. 500 atmospheres. So the first thing that I have to take into account, of course, I have to avoid leaks and the entrance of water. It has to be very well protected, but I have also to take into account the high pressure. And with this sphere, we are protecting the eyes and the electronics of the telescope that are inside this glass sphere. Yes. Πες μου πάλι γιατί δεν σ' άκουσα.
In Marianne Trans, how many atmospheres do we have?
How many atmospheres?
Yes.
You mean at 11,000, at about 11,000
Yes.
meters? We said every 10 meters is one atmosphere. So in 11,000 we will have 1,100 atmospheres pressure.
Oh.
Okay?
Yes.
Every 10 meters, one atmosphere.
Okay.
Okay?
Thank you.
Here we are, let's say the references I'm making are for the first neutrino telescopes. The first neutrino telescopes were installed in Pacific Ocean in Hawaii at about 5,000 meters. The second one in the Mediterranean Sea at about 4,000 meters. And also there is an effort that is still going in Siberia, in Lake Baikal, where they are installing the telescope at the bottom of Lake Baikal, which is about 1,000 meter deep. But we will see that we are facing significant problems in deploying these detectors in the sea. Before going on to the construction of the telescope, I would like to focus though on the construction of the eyes, because these are the crucial parts. These are the detectors. And here, although it's a neutrino detector, again it has to detect light. Very faint blue light that appears while the muon is crossing the seawater. So, what is the photomultiplier? This is a photomultiplier. In principle, is a device that is able to see only one photon, and is transforming this photon to a strong signal that we are able to record and say, yes, there was light in this photomultiplier, in the other photomultiplier, and so on, and we will be able in this way to reconstruct their track. Here, on the photomultiplier, there is a specific material. It's called photocathode. So this material, in principle, is going to transform the photon to an electron. Every time a photon is hitting on the photocathode, an electron is going to be produced. We will have a whole lab after lunch focusing on this phenomenon, especially what is happening here. And from here, because I need a big surface, because I would like to have a lot of high chances to detect the light, so I'm looking for photomultipliers. I'm using photomultipliers that they have very big cathode, not a very small one, but a very big, in order to collect light that is coming from different directions. Then the electron has to travel this distance, which could be about, let's say, 20 centimeters, to reach the amplifier. This is really the place where the signal, the number of electrons will be increased significantly in order to give us a clear signal that a photon was detected. Here we have a simulation. Here is the photocathode. Okay, so you see it has a radius of about 20-25 centimeters. Here is the amplifier, and here is the track of the electrons from the moment that they are produced till the moment they are approaching the amplifier. Can somebody tell me why here the lines are so close and then the distance between them is increasing? Why here there is a small curve while they seem to go straight after that? You see, it has this pattern again and again. Yes? The speed is increasing. Okay, and why the line is curved in the beginning and then it's it looks like more straight?
So, from what I can understand, they appear to find a straighter path. I'm not sure why, though. I just want to answer why are the dots like. I'm not sure about the second part.
So this is clear. You know, it's like accelerating particles, as we saw in previous lectures. So in the beginning, they are going slowly, and then the speed is increasing. So if I'm able to take their position, to take an image, let's say, in a specific time interval, I will see bigger and bigger distances. So this is why they are accelerated. And here they are accelerated because of this field. Here I need a very strong electrical field in order to push, let's say, these electrons to go to the center. But why they're turning, at least in the beginning? When the speed is not so big, the impact of gravity. The gravity is really very small for them, but it could be the way that you are thinking is very correct. The nature of the force is different. It's not gravity. Is because of their electrical charge, they No, these are all electrons. These are all electrons. These are not. Here we are inside the photomultiplier. The photon is coming from here. A photon is coming from here. Is interacting with the photocathode. Is interacting with this material here, and is producing an electron. So while the material of the photocathode, I think Eleftheria has shown this graph in her presentation. There is a photon coming, is interacting with the electron, and the electron is leaving the atom. Okay? So this is the electron here. The electron produced on the photocathode. There is a very strong electric field that accelerates the electrons. The question here is why there is this curve in the beginning of their track. due to
Due to electromagnetic forces from materials around the sphere? Maybe?
It's because of the Earth's magnetic field.
Oh.
Okay? It's the Earth's magnetic field that is really in the beginning when the speed of the electron is very small, it has a significant impact. But our effort here, and this is very important, this is a simulation where I see 10 electrons. But imagine I would like to detect only one photon. So it's very important not to miss anyone. So if the curve here is bigger, maybe it's going to lose the amplifier, and then I don't have signal. So I have to protect the photomultiplier and reduce the impact of the magnetic field. That's why I'm using this net around it. So in this way, we are inducing the value of the magnetic field inside the photomultiplier, helping the electrons to follow a straight line from the photocathode to the amplifier. Okay, so these are some efforts from the sea, because you have to make many tests. You have to make many efforts to see if in principle is working, what other sources of noise I could have deep in ocean, how easy is to lower the detector, how I'm going to make the connections, how, if something is not working, how I'm going to get it back. All these are very, very important issues. So here you see a part of the structure. I will come to the structure of the telescope. You see the photomultiplier. It is covered inside, protected inside this glass sphere, and in this cage to reduce the magnetic field. Our initial efforts, let's say here we are located somewhere there, Thessaloniki is over there, at the southwest of Peloponnese. This is the African plate entering under the European plate. So very close to the shore, there is a very deep, I would say, field where the plan was to implement this detector. The depth there was 5,200 meters. Here is the landing. This is from the first efforts back in 1992, 1993. A Russian research vessel came to the Mediterranean in order to make this kind of tests. So here you see the structure, you see the different optical modules as with the detectors. There are detectors in the center, there are detectors at the end of the arms, and as all this structure is going inside the water, because of the force of buoyancy, is opening and is becoming like a star. This is the overall structure, 2 floors of the telescope. Here is 1 floor, one of them, and here is the whole construction. So 300 meters high. You see the buoys up to keep it to keep the different floors separated. Here are the optical modules at the end of the arms. Here a very big sphere made of titanium to host the electronics of each floor, and all the messages through cables are going back to shore through an electro-optical cable, about 36 miles away. So the detector is operating at 5,000 meters under the seawater, under the surface of the ocean, and the messages are transferred to the shore. This is the current phase of development. It's not taking place exactly there. It's about 1,000 kilometers away near Sicily, because now the different teams, the different groups from Europe came together, Italians, French, also Germans, there is a Dutch team and so on. It's a major European effort, and they are constructing this detector that is called kilometer cube network neutrino telescope. Kilometer cube, because we need really a very, very big detector in order to observe neutrinos that are coming from all these sources. Plus, you see that they are using a different structure. Instead of having these arms that in the initial phases it was quite difficult to accommodate and to handle, especially from the ships in the moving let's say platform of the ship. Now there are in principle strings with photomultipliers that are deployed at different locations. And for each one of them, there is a line that is connecting them to the electro-optical cable that is transferring the information. Also, the initial idea of the photomultiplier, of the big photomultiplier, has been replaced by using numerous smaller ones, which are more effective, and all this effort of making sure that all the electrons will arrive to the amplifier and so on is not necessary, because these photomultipliers are much more effective. So this is the current situation. Manoli, would you like to say a few things for this detector?
Yes. Okay, so what you saw before with the stars and the titanium arms, this was the Nestor experiment. This was the first one that started to take place in the Mediterranean, in which Dr. Sotiriou was part of, also myself later. And here, to the left, you see the so-called Antares experiment. This one was in France. Now, I want you to pay attention to something. You want to detect a neutrino coming, let's say, this way, okay? So a neutrino interacts here. It produces a muon, which goes there, and this produces Cherenkov light, right? As you saw before. So what you are actually detecting are these faint blue flashes coming here, and so on, okay? So you need to have a very, very big volume instrumented with these eyes, okay? And you also need to have very clear water. The French don't really have that clear waters. In Greece, it was a bit better. You want clear water, why? Because you want the light to be able to travel for a long distance before it's being absorbed. So, historically, Nestor was the first. After that, the French Antares and the Italian R&D started for a few years. Antares was the first, let's say, completed neutrino telescope, which, however, didn't detect neutrinos from the cosmos. And all these efforts converged in Europe in around 2006, 5, 6, and so on, in order to build this very, very big kilometer cube detector. KM3net means 1,000 times 1,000 times 1,000 meters. Okay? So, this way, first of all, you have these small eyes, which means that you may be able to track particles of lower energies. For example, maybe be able to infer the existence of supernova neutrinos also, but also you have a very big instrumented volume in order to be able to track very highly energetic neutrinos from the cosmos. So right now, the KM3 net has two sites. It's built in two locations simultaneously. One location is outside Sicily, in Catania, in which the waters are more or less as good as the ones we have in Greece. And there they are building the big detector called ARCA, Abyss something, I don't remember. So the ARCA array in Italy is a very big neutrino telescope which is being deployed every 6 months or so. And there they hope to detect, we hope to detect actually, neutrinos coming from the cosmos. In France, they have the old Antares telescope, and they have packed it with more photomultipliers in order to have the ORCA array. ORCA is a very densely packed array of such eyes in order to be able to detect muons traveling short distances, which means neutrinos of lower energy. Therefore, you have an array to detect low-energy neutrinos coming from the cosmos, GeV neutrinos, and an array trying to detect very high-energy neutrinos coming from the cosmos. And why is this important? Because they come from different phenomena. Very high-energy neutrinos may come from GRBs, may come from active galactic nuclei, may come from very highly cataclysmic cosmic events. GeV neutrinos may come from protons impacting the atmosphere and being produced there. So you want to discern different types of phenomena. ORCA will be able to do oscillations as well. I talk too much. Any questions? No, okay.
Okay, the other case, I would say, is the other case are the ice cube detector. Okay, the ice cube detector, neutrino detector, is located in Antarctica. So here is the surface of the ice. And again, they are using the same approach. They are lowering strings with optical modules, with photomultipliers, aiming to see neutrinos that are traveling, they are crossing the ice. The ice is not, let's say, so clear as the seawater. In fact, if they go at higher levels, the ice has bubbles from its creation. This ice is there since the creation of the planet. So here, the pressure, when it was created, it was not so big, so there are bubbles. So in principle, the light is going to make, it's going to change direction many times. While here, at the very bottom, as when this ice was created, because of the dust from the volcanoes and the dust that was falling on the planet, is not so clear. So it is located, let's say, at about 2,000, 2,500 meters. So not so deep like in the ocean. On the other hand, there is a significant advantage, the stable ground. They can work anytime, there is no ship, there is no need for a moving platform and so on. They are bringing their machinery, they are opening the holes, and then the detector is there for forever. This is a picture from the process of lowering the detectors. inside the deep hole. They are opening the holes with hot waters, with very hot water, and they have about 2 or 3 hours to lower the whole string there before it's freezing again. This is the station. This is a publication. Here we have the opportunity to see really how the muon is coming in this publication. This is from 2013, where the work was still in progress, but we had some proof of concept experiments. So you see, in principle, a muon is coming in this direction, and while it's passing across, these detectors are not seeing the muon, but the blue light that is created from this cone of Cherenkov light. So these were activated, this, and here a lot of detectors, because the muon is going very close to the detectors there, a lot of light is produced. The size and the color of these spheres is directly related with the amount of light that these detectors are detecting. So these have seen not so much light, while these ones, they were really activated. And of course, they have managed to detect some very, very high energetic events. These are some examples from, you see, this is 4,450 TeV. It's a very, very high energetic events. Remember, 14 TeV is the maximum energy that we can give to the particles to create when we are creating collisions at CERN. In principle, we are giving them 7 TeV and 7 TeV to the other proton. Here we have events with 4,450 TeV. So the question remains how these so energetic particles are created, where? And these are created in these cosmic, as we call them, accelerators, cosmic accelerators. Here, in principle, this is the core of a galaxy, an image of a core of a galaxy where all these materials, let's say, are rotating in very high speeds around the center of the galaxy, and there is the production, I would say, the production place of these high energy neutrinos. So this is an example, let's say, of this process, how when these materials are interacting with the dust, they are finally producing the neutrinos that are leaving from this cosmic accelerator. And in fact, if we are able to track back and reconstruct their direction, their track, we will be able to create a map of the sky with these sources. In 2017, September 22, the IceCube announced a neutrino carrying an energy of 290 TeV. Comparison, as we said, the energy from a particle on LHC that can be generated in LHC could be up to 13 TeV. So there is a cooperation with astronomers. So we are trying to create an alternative map of the sky, locating all these sources of high energetic neutrinos. And as Dr. Vourlias came here to stop me, I had my last slide ready for him, and I have presented. So That was our presentation with Manolis from, let's say, from this, let's say, alternative field of astronomy using neutrinos, and the very big efforts that scientists across the globe are making to, let's say, to identify all the parameters and the characteristics of these particles and use them as carriers of the messages from the universe. Just to summarize, before we have the opportunity for some questions, we said with conventional astronomy, we can see up to 400,000 years after the Big Bang. We are using for alternative ways. In the first day, we have seen the gravitational waves case. Today, we will have also a lab about that to see how this detection technique is working and which is the basic idea behind the construction of gravitational waves detectors, because we can see gravitational waves coming directly from the Big Bang. Another option are the neutrinos. Still a lot of work to be done, but the proof of concept experiments are there demonstrating that in principle the technique is working. And the third and the most successful up to now process is to simulate the conditions immediately after the Big Bang at accelerators like the Large Hadron Collider at CERN. So we have tried to offer you an overview of all this process. Thank you. Questions?
Are there any other sources of high-energy muons that can cause interference, like other kinds of radiation, for example?
In fact, the atmospheric muons are really our main problem. The atmospheric, the muons, in principle, this is also in, it was presented also in the school book of the third class of Lyceum in the Greek curriculum as the case that demonstrates a clear demonstration of the special relativity. The muon is created, let's say, at the upper levels of the atmosphere. In principle, it should never reach the bottom of the sea because its lifetime is not enough. But when it is moving, as it is moving with a relativistic speed, it can reach the 5,000 meters underwater. So it lives more. So it's making a bigger distance. So it's a major background for our detector. So these muons that have been created in the atmosphere are bombarding our detector. In principle, a detector like the one I have presented, a tower with 300 meters height and 30 meters diameter, is receiving about 1 million atmospheric muons, is detecting 1 million atmospheric muons in one day, and only one muon that is coming from the bottom, and it is related with a neutrino. So I have to be able to discriminate between these 1 million muons that are coming from atmosphere, and they are not signal, they are noise, to only one muon that is coming from the bottom, and it is the signal I'm looking for. That's why all the photomultipliers, the ones that I have presented, and also the ones that Manoli showed from the new experiments, are looking down. They are not looking up, in order to have less light that is coming from muons from above. Okay, so this is the major background for these telescopes, the atmospheric muons. Okay?
Yes, thank you.
Yes, please.
In the experiment you talked about in France and also in Greece and Italy, is there a specific reason why you place the machines like in a line and parallel to each other? And will this placement affect their work, or?
In principle, what we would like is to create a box and fill it in with photomultipliers everywhere. This is the ideal case, to create a cubic kilometer of detectors. So the distance is very important, because the attenuation length, the distance that the light is traveling inside the water, of course this is highly dependent from how clear is the water. In the seawater is about 50 meters. Okay? So if the light is created here, and then I have, let's say, to put the next detector there, the other there, and so on. In principle, I have to keep in mind the parameters of the medium. If I'm in seawater, here, let's say in Greece, it was 30 meters. Why 30 meters? It has to be significantly less than 50 meters, which is the attenuation length. So the distance between the floors was 30 meters. The distance between the diameter, let's say, was also 30 meters.
So they don't affect each other's work, but instead they are like creating a box.
Exactly. So to make sure that everything that goes inside this box or in this cylinder is going to be very well defined. Okay? But if we are in the ice, if there are bubbles, you see the attenuation length of the light is going to be decreased. Maybe it's 20 meters. So then I have to bring the detectors closer to make sure that I'm detecting. Otherwise, you know, the light will go this direction, is going to be detected, then it's changing because of a bubble, it's going there, then it's going to be a mess.
Okay, thank you.
Okay, so it's geometry, it's the nature of the way the light is traveling, but also I have to take into account the parameters of the medium. Okay? Other question? So Mr. Vourlias is making an evaluation of this course, and he's counting the number of questions after each lecture. So give me questions, because if I don't have many questions, I'm not going to take a good mark from Dr. Vourlias.
Yesterday he had 20 students here.
You see, we lost already, Manuel. We had only 3. So give us questions.
We talked about the reduction of speed of light when light goes through water.
Yes.
Do we have any reduction of speed of the speed of neutrinos when they go through objects, solid objects?
There is no reduction.
So it's the same speed when they go through Earth and when they go through vacuum?
Yes, yes. And also for muons. The muon is going with the same 0.8 the speed of light. If it is in the atmosphere, if it is inside the Earth, is not decreasing the... That's why it is producing Cherenkov radiation. Okay? The speed of the muon inside the water, the seawater, is higher than the speed of light in the seawater. Okay? The speed of light, you have to take c divided by n, where n is the refraction index of the medium. Okay? So in this way, you can find how much the speed is reduced. in principle, muons are creating Cherenkov light here, this moment. But it's so faint that with all this light we are not able to see it. Okay, the Cherenkov radiation is here between us, because they can create this phenomenon. It's not so strong as it is inside the water, because there I'm in complete dark and I am able to see that. If you go to there was especially for the Greek students, there was an experimental reactor in Democritus in Athens, where there was a big tank where it was the students were able to visit it, and it was the light inside the tank was completely blue. It was because of the Cherenkov radiation.
Second. Okay. Since neutrinos have mass, do they get affected by gravity?
In principle, if let's say the field is so strong, it will be affected. But still, as I said, we don't know exactly how much mass, because they have very small mass. We only know the differences between the masses of the different types of neutrinos. We don't know exactly the mass of each flavor of the neutrinos.
Since they are moving at the 0.8 speed of light, they only supermassive objects.
They are moving even faster. Muons are moving with 0.8 of the speed of light. Neutrinos are traveling with almost the speed of light. That's why they were always candidates for being the particles that can go faster. So they are moving even faster than the muons.
Thank you.
Could you tell us how neutrinos are created? I think you mentioned already some ways they are created. For example, when they interact with dust around black holes, or I think with the nuclear fusion in the sun as well.
Also in all these processes here. So you can see in this all interactions where you see the production of neutrinos. How they were discovered? They were discovered back in 1930 as a product of beta decay, in order to make sure that the energy conservation principle is still valid, as we have seen from the letter of Pauli. So in beta decay type. In nuclear, in principle, they are produced in nuclear reactions.
Okay, so basically, and as I can see, I think also when some particles gain energy, so, are they emitted like electrons in a similar fashion, or do they have like a different nature?
If they are emitted like?
Are they emitted in the same fashion as electrons, like when some particles receive energy, or are they completely independent?
In principle, they are produced in the same process. You see, here we have a positron and an electron neutrino. While in the opposite process, we can have an electron and antiparticle, the antineutrino.
Okay.
Okay. So to keep also the lepton presence at the same level.
Okay. Thank you.
Okay. In principle, they are forming the category, as we said, of leptons: electrons, muons, and tau. Electron neutrino, muon neutrino, and tau neutrino. These are the leptons. Everything in the nature, in the matter, consists of leptons and quarks. Okay? This family, these are really basic particles. electrons, muons, tau, and their relatives, the three flavors of neutrinos. These are the lepton family. Yes, please. Please. Eh?
So you mentioned...
Sorry, he counts the number of questions, so we need more questions. Okay? We are close now to the yesterday record.
You mentioned anti-neutrinos. Neutrinos have no charge. So what exact difference do neutrinos and antineutrinos, if not the charge? What difference in quantum numbers and properties do the two have?
It's the spin, which is negative, and in principle, when you have what is happening, what is the matter and antimatter, when they are coming together, they disappear. So this is the key characteristic.
It's not so the lack of charge doesn't make a difference here?
No.
Okay, thank you.
Yes, please.
I read about some minutes ago something about muon tomography. I'm not sure what it is and what actually is happening with this. So can you explain this to me? Muon tomography.
By the way, muon tomography has been used from a research group, I think, here in Thessaloniki.
I read it now on my phone because
Yes.
I shared about music.
It's in Thessaloniki.
Oh.
You know, it's a process that they are using to identify if there are holes in big hills looking for the tombs of ancient Macedonians here and so on. So also how they are studying the internal part of pyramids in Egypt.
So they use it like in places like...
Yes, why this is happening? The muon, let's say I put a muon generator, let's say, from one side, and I have a very big box, okay? The muons are crossing the matter, so some of them are going to, let's say, make a smaller part because there is an empty space inside.
So it's like cutting the muon.
It's like cutting an object and looking inside, but instead of making it, let's say, with visible light, to see with muons.
Okay.
I'm using muons, so I can see a hole, let's say, there, exactly where the hole is expected to be inside this mountain.
Okay.
I'm able, let's say, to identify that there is something there. I don't know exactly.
So can we also use it from distance?
Yes, of course.
And how long distance exactly can we?
This depends from the efficiency of the detector that I have every time, and how sure I am, because
and the distance,
as I told you, there is a very big number of muons that are coming from the atmosphere and so on. So the background is very, very, very high. So I have to make some specific experiment to identify, let's say, a cavity inside an object. This kind of things. This is what we say tomography. Tomography is also, apart from the way that we are making tomography in the human body, is a term that is being used in seismology, for example. We are using the seismic waves that are coming from different parts of the world in order to see if there is some cavities underground. That's why when you hear that there are some surveys in the different places and they say seismic research, in principle, it's related to the detection of areas where there are cavities, so it's maybe a source of petrol and so on. So in this way, they are able to identify places where they have to dig in order to get gas from the from underground. So we are using the seismic waves to make a tomography of the Earth. It's a term that we are using. So a quite interesting technique, and I think it was here at Aristotle University that they made this experiment. They were using...
They still use it.
I don't know. I don't know if the experiment is still running, but it was a van. Okay. They were going next to a hill. Here they call it tumbas. Tumba is the tomb. No, the tomb. So they were sending muon fluxes to see if there is a cavity. If there is a cavity inside the hill. Okay, you have to report that. Okay. Okay. I would be happy to discuss with you if you have further questions during lunch. During lunch.
Mr. Kanyotakis, let's make a serious announcement for the
Wait. Good. So, we will be again divided in two groups as we did. We will be divided again in two groups as we did the days before. So, the team of the Balkan students will be coming here at 2:15 to work with me on gravitational waves, together with the names that you will hear now. Anagnostopoulos,